Oh, hey guys.
Hey! What's wrong?
It's just, I can't really figure out how to do this math problem.
I'm pretty good at math. I think I can help you.
Yeah, we can help. You can... No.
Yeah, so, no, never mind, that's right.
You know who we need?
Professor Dom!
It's time for calculus.
Dom is the coolest. He will teach you math. Dom is the coolest. He will teach you math. Trish. Jordan. Tyler. And Dominic. And this is Professor Dom.
Hello everyone, I'm Professor Dom and today we will be learning numerical series. So I'm just going to do a quick review of all the stuff that we've learned in this unit. So the problem is determine whether the summation from 1 to infinity of 1 over pi to the n is convergent or divergent. And so we just have to remember our rule for geoseries. If the summation from some number to infinity of r to the n, if the constant r is less than 1, we know it must converge. So let's look at this one. We know that r is 1 over pi here, and that's less than 1. And so we know it converges by the geoseries because r is 1 over pi, which is less than 1. Our next test is the telescoping test, and this one is very terrible. I'm sorry that we have to do it, but... So the question is determine whether this guy is convergent or divergent. The first step of a telescoping series is always to PFD it and break it up into its PFD form. So we just make this into its two parts. N plus 1 times n plus 2 is n squared plus 3n plus 2. And then PFD, we don't have time to go over the PFD, but we get to summation from 1 to infinity of 3 over n plus 1 minus 3 over n plus 2. Then we write out all of the terms. So we get to here and we can see all the middle guys end up canceling. So we're left with the two guys on the end. And because we're taking the limit, this 3 over n plus 2 goes to 0. And we're left with 3 halves. And because it converges to a number and not infinity, we know it converges by telescoping. So here's a nice example that we can use the p-series test for. It says determine whether the summation from 1 to infinity of 5 over Dom to the 1.2 converges or diverges. And you have to make sure Dom is only natural numbers, blah blah. So we remember our rule for p-series. It's if the summation from 1 to infinity of n to the p, if p is greater than 1, then it converges. If it's less than or equal to 1, then it diverges. We all know the special case of 1 over n, just straight. We call that the harmonic series, and a common mistake here would be calling harmonic series its own test. So for this one, it's pretty obvious that it converges. Our p-value is 1.2, which is greater than 1, therefore the summation converges. Alright, here we've got an example for the divergence test. Determine whether this nice guy is convergent or divergent. One thing to quickly remember here, if the limit does go to 0, this does not prove anything about convergence, it just proves divergence. We can't say anything about convergence if this thing is false because we don't want to be the ones to make for our rage quit while he's grading. So the rule is if the limit as n approaches infinity of a to a sub n, which is this guy, if that does not equal 0, it diverges. So we'll take the limit as it goes to infinity of this guy, factor it out, 3 to the n squared plus 3n over 2n squared, and we know that limit goes to 3 halves because of the biggest powers. And 3 halves coincidentally does not equal 0, so that does tell us it diverges by the divergence test. Next test we're going to do is the integral test. This one's pretty weird. We're going to convert this summation into an integral, and we'll use that integral to estimate the summation value of this, and if the sum is infinity, we know it diverges, and if the sum is the number, we know it converges. And a common mistake people will do is they'll find the value here and they'll say that's the sum, but that's not the sum, it's just an estimate of the sum. So I turn it into this integral 1 over m times 1 over ln m dm, and I just picked m as an arbitrary variable, and then we do a simple dom sub right here. So when we solve that down and plug in the bounds, we end up getting infinity minus ln of ln2, and that's just infinity, so we know by the integral test this whole guy diverges. Our next test is the direct comparison test. So it wants us to determine whether this guy here is convergent or divergent. To do that, we're going to find something simple that we can easily compare to this guy that's not so complicated, and see if that tells us anything about convergence or divergence. And a good tip I like to do is I like to get rid of all the constants and just see what this is behaving like. So this is behaving like e times n over 4n cubed. So let's compare it to that guy. This isn't going to work every time, but this time it works nice because this value is less than the one we're comparing it to, and the one we're comparing it to converges by the p-series. This one also must converge because it's going to be a less finite number. So we say this converges by p-series. This must also converge by dct and p-series. So for the limit comparison test, this one's a lot more useful. You can use it a lot more times. The logic is, if this guy divided by a thing we're comparing it to equals a number, this original guy will behave like that guy when n goes to infinity. And so to make an easy comparison to 1 over n minus 3, I compared it to 1 over n. There, I took the limit, copy dot flip it right here.
Please, no! 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 No!
And that equals 1. That is a number. Nice. That means this all must diverge because we know that 1 over n diverges. Our next test is the alternating series test. This is a tricky one because a lot of people are going to want to use it just to prove that something converges. And it is a proof of that, except it only proves if it converges conditionally. This is best used after we found that the absolute value of this guy diverges. So there are two conditions that have to be met when using alternating series test. The limit as n goes to infinity of this guy has to equal 0, and nicely it does, and it has to be decreasing. This guy's a beast to prove whether it's decreasing. We just take the derivative of the absolute value of this guy and we work down its derivative, and we see that its derivative in the end is a negative, so it must be decreasing. It must converge conditionally by the AST. Here we've got the root test, and it's asking whether it's convergent or divergent. This one behaves in the same way as the ratio test does. We take the limit as n goes to infinity of something, and then if it's greater than 1, it diverges, and if it's less than 1, it converges. And what's important to note here is that if it equals 1, it's non-conclusive, and we have to use a different approach. For the root test, we just take the nth root of it as n approaches infinity. The n's cancel out in this step. It equals 3/5 as n goes to infinity, and that is less than 1, so it converges by the root test. Ratio test. This guy is the same as the root test, except we're taking a different value as n approaches infinity, but it's the same thing. We're taking the ratio of a sub n plus 1 over a sub n. We plug in n plus 1 into the function here. We get n plus 2 factorial over 3 to the n plus 1 over our just original guy. And now keep change.
Please, no!
We can separate the n plus 2 factorial into n plus 2 times n plus 1 factorial, and the 3n plus 1 to 3 times 3 to the 3n. We cancel these guys out. we get limit as n approaches infinity of n plus 2 over 3 equals infinity. That is greater than 1. Therefore, diverges by ratio test. So now we're going to be looking at the annoying ones. It's asking what this sequence ends up converging to. The way to do that, it's really just a rephrasing of take the limit as n approaches infinity of this. We're going to set y equal to the limit as n approaches infinity of this one. And as we remember from Calc AB, this is a mean problem. So we take the natural log of both sides, get ln of y equals n times ln 1 plus 1 over n. And the n just comes down from the exponent because that's the natural log rule right there. And right here we get an infinity times a 0, which is ugly. Let's make it 0 over 0 so that we can L'Hopital it. It's still ugly, but now we can L'Hopital it and hopefully make it more beautiful. So ln of y equals ln of this guy over 1 over n. We just brought the n down, so L'Hopital, proof, L'Hopital. Then we take the derivative on the top and bottom, we get those nice little guys. Bring the n squared to the top. This limit goes to 1. But, don't stop! Good job, notes. I was about to stop. This is a very common mistake. I just made it, pretty much, if I hadn't had that step on my paper. That's what ln of y is equal to. That's what ln of y is equal to 1. Y isn't equal to 1, so our answer is E. Okay, alternating series estimation time. Gross, I agree. What we do for this one is first we have to find how many n values we need to use to estimate into our calculator. And we want this whole guy to be less than 0.005 because that's equal to 2 decimal place of accuracy. And we set it equal to it to find it. And solve, n equals 5.848. So what does that mean? Is n 5, is n 6, is n 5.8? Well, clearly it's not 5.8, because 5.8 is not a natural number, if you did not know. But what do? For the alternating series estimation, we always round down, and we round down because it's telling us our next jump is within 0.005. So if our next jump is within 0.005, we're already close enough to our middle value that we want to be to. We just plug that into our calculator from 1 to 5, and we get negative 0.90. Alright, now we're going to do our last problem here. Estimate the sum of this guy using an n value of 3 plus 4. Then find the error. So the first thing we want to do, what is 3 plus 4? That's 7. So it's just asking us really for the first part to plug in 1 to 7 on our calculator. And we get this number. That's the estimate from 1 to 7 is 3.024. And then the next part, we want to check our accuracy. We know that r sub 7 has got to be less than the integral from 7 to infinity of our guide. So we can take the derivative here. We get negative 2 over dom from 7 to infinity. And little technically box here is being all annoying. He's saying, technically it's a limit as m approaches infinity of negative 2 over dom from 7 to m. Well, yeah, you've got to do that for the points on the test, but it's annoying. So you get negative 2 over infinity minus a negative 2 over 7. That's just 2 sevenths. So 2 sevenths, which is about 0.286, is the max error. Alright, thank you guys so much for watching this video. And this has been our calc project. Thanks.
Dawn Productions.